Hello everyone. Today I'm going to talk about a keyboard that I built from scratch, including the design, the soldering, the building, layout, all of that kind of stuff. I also did a bunch of other stuff like genetic algorithms for designing the layouts, and I did write at least half of an auto router to do the routing, although I didn't end up using it at this point. And also I can go through the kind of electrical engineering principles of a keyboard in another video, so let me know if you're interested in any of that. But for now, what I'm showing here is the soldering after I've designed the PCB and then got it fabricated. You can see here I've got like a kind of janky setup for sucking away all of the solder smoke. So the thing about soldering is the rosin in the solder, the rosin, the flux, which makes the solder wet more easily, burns and it produces the smoke, which smells extremely nice and is very nice to smell, but is probably not very good for you and also may give you asthma or something like that. So it's good to suck it away. Here I've got a Dyson vacuum cleaner connected up to a aquarium filter that I filled with a HEPA filter and a bunch of activated charcoal. And I'm using that to, and a silicon tube, and I'm using that to suck away all of the smoke. And I've also got like a little fan here to blow away the smoke as well. And I think I'm wearing an N95 mask as well in this. So I would say the main danger with soldering is the smoke from the rosin. I am using a 6040 leaded solder. The lead is not really an issue here. So the vapor pressure at lead at soldering temperatures, like 200, 300 degrees Celsius, is very low. So there's no real danger of lead poisoning from inhaling lead fumes, so like boiled lead. There is a danger if you're doing what I'm doing, which is soldering in your kitchen and living room. You have to be very careful that any lead solder dust does not get onto your hands or otherwise into your body through like ingestion. So if you solder in a living space, definitely you got to wipe down all of the surfaces afterwards. For what it's worth, I've been doing stuff like this for years and years and years. Also while I was a kid too, and for kids, lead poisoning is much more of a concern. The allowed levels for consumption of lead in kids is much smaller. But I tested myself for lead poisoning and other heavy metals, and it's all normal. So it's definitely possible to do this kind of stuff in your living room without doing yourself an injury, but there you go. So as for the actual keyboard, what I'm doing here is I'm putting in sockets. So you got your keyboard, right? And then you got switches. The switches are the things you press. You got like your cherry, MX reds, your browns, Gatorons, etc. And you gotta connect these switches to the keyboard somehow. And I've elected here to use sockets. And the reason why is because you can like hot swap these sockets. And if like say one of your switches breaks or you want to try out different switches, it makes it a lot easier and than desoldering an entire switch and then putting another one in. You got to break out the soldering iron. With this one, you just chuck them into the socket. The sockets are rated for some number of insertions and removals. I don't think it's like a huge amount, maybe on the order of hundreds, but it definitely worked for my purposes. The only issue here, at least for me, is that if you solder the switch in, you've got kind of a mechanical connection, right? Like the solder connections are relatively large, so they do have some degree of mechanical strength. If you've just got it plugged into a socket, you definitely need something to hold the switch in. So I've got like a top plate. So kind of a plate that goes on top of this with square holes that fit around the switches, and the switches themselves have clips and they're meant to clip into like this kind of top plate. I think for keyboards, these top plates are often made of like some kind of metal, like aluminum or whatever. But what I did to kind of reduce the cost and make it easier is I made this entire keyboard out of PCBs. So you've got the top plate, which holds the switches, and that's just a PCB. And you can put in like all the holes and stuff, and the PCB fab will cut it out for you, so you don't have to bother with getting something created separately. And then I've also got a bottom plate that I put below this, and I connect it together with like these screws and kind of nuts. I think I'll show it later in this video. So that's kind of one portion of it. And here you can see I'm doing like a test fit of the switch into the into what I built so far. So I've got the sockets in, and now I think I'm putting in the diodes. So the reason why you have a diode is this is maybe better suited to a video explaining the electronics in detail, but that basically you have the switches in a matrix. The matrix has rows and columns, and you query the state of each key over time by looking at the row and the column. So if you've got n rows and n columns, you've got n squared combinations, order n squared combinations, and you query each key to see if it's on or off. And that allows you to get by with you got like n squared total keys, it lets you get by with approximately n electrical connections. But you have to like kind of multiplex your querying over time. So you kind of split this dimension that you would normally use on n squared electrical connections into like n things over time. And the reason why you need the diodes, going back to the diodes, is since you're querying stuff in a matrix, the matrix, if you didn't put diodes in, kind of the electrical connections between like a row and a column can connect to other switches if they're also pushed down. And you'll see this on cheap keyboards, but you can't press like more than some number of keys at the same time, say like 6 keys at the same time. And the reason is because they didn't put enough diodes into the keyboard. So you press like an extra key down and it doesn't generate like a state. So if you imagine the state as you query a bunch of rows and a bunch of columns, it doesn't generate a state that's different, so that you can differentiate like more than that number of keys pressed down, or like which ones they are. So I've got diodes on every single switch here, so I can query every single switch, even if they're all pushed down at the same time. Now I'm going through and checking in, I think this is LEDs and capacitors. So I've got LEDs for each switch, and the point of this is so that you can display a color for each key. And I use like different colors for different kinds of keys. So like they're A to Z can be like blue or whatever. And then when you switch the layer of the keyboard, so I got like a layer for like symbols and like a layer for numbers and a layer for like function keys, etc. You switch the layer, then the colors will switch. It'll remind you which kind of key it is, and also remind you which layer you're on. So it kind of has a dual usage there, which is pretty nice. And as for the capacitors, this is probably like overkill. And I also had like 1,000 0.1 microfarad through-hole capacitors lying around, so I just decided to chuck them all on. But at least it's good to have capacitors near things that are going to be taking sips of current, like these LEDs. If you turn them on and off, they're going to require some current, and it's nice to smooth out the voltage near these things. This is probably not really a concern with a keyboard like this. So you've got the microcontroller. It's going to be querying these keys to see if they're on or off, but it's not that fast. So it's not like really high-speed electronics. And you have these LEDs, but they're probably not that sensitive to voltage fluctuations, I would guess. So this is almost certainly overkill. But, whatever. I get to use up some of these caps that I bought, and I have 10,000 of them, so yeah. Now I am chucking in some resistors. So this is a split keyboard. I'm using QMK as the firmware, and you can see also there's the TRS socket jack, which will connect the two sides of the split keyboard. Now, the reason for the resistors, they're actually pull-ups for the I2C communication between the two sides of the keyboard. So I'll use basically a headphone cable with 4 wires in it to connect the left side of the keyboard to the right side of the keyboard, and it'll communicate via I2C to relay the information like which keys are pressed. So the other side of the keyboard needs to know which keys are pressed, so it can know which layer it's on, and also if shift is pressed, it will change like the keys and also like the LED state that the other side of the keyboard needs to show. Now I built it and I plugged it in, and of course it doesn't work. Only 3 LEDs are shining. So probably this is an issue with just like a connection is not done correctly, but it is possible I destroyed one of the LEDs. I did accidentally burn a couple of them with a massive soldering iron I was using. So there you go. So I break out the oscilloscope and I just want to check that we're getting signals that make sense. So you can see here we got like a kind of a square wave, and that makes sense when you imagine that the microcontroller is going to be querying each row in each column. So it's going to briefly, drop the voltage on one of them to check if any like current comes through. Anyway, I think I fixed all of that stuff, and here I'm wiping off all of the old flux. And I mean, again, this is not really necessary, I think, for this level of like electronics, but the flux does have some like electrical characteristics that can cause issues. Like you can have at like stray capacitance, I think. So if you're definitely if you're doing like high speed stuff, you want to do this just for a keyboard. I mean, I just want it to look nice and shiny. I'm using isopropyl alcohol, so 100% isopropyl alcohol to get off the non-polar stuff, and then I'm using distilled water to get rid of everything else. If you only use isopropyl alcohol, you end up with like a white like fuzz all over your PCB, which looks kind of trash. So isopropyl, then distilled, and then dry it out. Make sure to dry it out before you plug it in. Even though you use distilled water, like you should still be careful. There's probably some like ions and stuff still hanging around. Now here's the bottom plate. I've got these screws and nuts, and the nuts are like I think 3 millimeters tall, and that makes a little space. So a little spacer between the PCB and the bottom plate. I connect that on, and I have holes for like a mounting system. I tried to do like a tented thing, put everything at like 45 degrees, and then you can control the angle of the tenting by changing how much the screw is in or out. I think in the end, I ended up getting rid of this because it was just kind of annoying to type on. But if I had like a better tenting system, maybe if I get a 3D printer, then this may go better. And I'm like testing it out. I don't know. I put some like silicone caps on the end of these screws to make it not slide around on the table. But yeah, in the end, I got rid of it. Oh, another thing is for QMK, you also got to code up your own firmware. It's not too hard, but if anyone's interested in, I can go through what I did for mine. But basically, it's just set up like which pins you're using, enable the options. I actually did implement a bunch of custom stuff. Like, they have a, mod tap kind of stuff. So like you can assign different functionalities. So if I hold down A on my keyboard, it'll send Control A if I hold it down for more than like 200 milliseconds. Otherwise, it would send a regular A. But the problem is like this can detect lots of different kinds of inputs, right? So like double tap, triple tap. And what that means is that if you only care about tapping once or hold tap to send like a Control A, sometimes it will need to wait for like an extra timeout to determine that this is not an input that is a prefix of any other inputs, right? So if you double tap as a prefix, it's triple tap. So if you double tap, it's got to wait a little bit to see if actually that's going to be a triple tap. And obviously can't read into the future, so it's got to wait a bit. So I implemented my own system. I called it hold tap. It just supports those two things, but the benefit is you don't get like this weird like latency where you like type a key and nothing appears until like a timeout happens, and it's very like jarring. If you only care about hold, you can just like release the key and then it knows it's done there. So here's some, static shots. The PCB is on the right. My janky setup for sucking away the solder smoke. Here's a close up of the PCB. And here you can see like the top plate, the bottom plate, and the PCB itself. And also here's the finished product.